Nice to see some other East Coasters. All right. So we will start to get started a little bit slowly here. My name is Jordan. I'm the moderator for this group today, but the real stars of the show are Sam Ritchie. You can give a wave, so in case we don't see your name, and Colin Smith. And another wave. Awesome. And we are going to talk today about the port of SICM-utils to Clojure and ClojureScript. So Colin helped make it happen for Clojure, and Sam is helping make this happen for ClojureScript. And it's amazing that we're going to tie all these ecosystems together. So we're going to talk about the benefits of these ecosystems and having it all in one place and having these tools. Colin, would you like to introduce yourself a little bit?
Hi there, my name is Colin Smith. I've been I knew I wanted to be a computer programmer since I was a little boy, but I won't go too far back. In the 90s, I was a C++ programmer working for typical industrial jobs, and I found one of the founders of the company I was working for had I guess gone to MIT, and so he left his copy of Structure and Interpretation of Computer Programs lying on a bookshelf, and I picked it up because I was bored, and I was immediately hooked by it, and I can genuinely say it changed my life. It was like a chance to relearn computer programming all over again. So when I try to tell people what's special about that book, I say that they don't get to the set command until page 220. And so up until that point, they've managed to discuss computer programming without mutating anything. And I consider that a tour de force. And of course, in a Clojure crowd, we've all heard Rich talk about this at great length and very persuasively. But I had this sort of queue up to that. And I went through the whole book of structured interpretations of computer programs and did all the exercises, including the sort of code generator and scheme compiler, where he talks about how this is all instantiated on real hardware, which was illuminating in itself. And so at the end of that, I consider myself a Lisper. And so when this odd follow-up, the structure and interpretation of classical mechanics, came along with that same mysterious lambda picture and a drawing of Isaac Newton working a prism, I thought, I always was kind of like many hackers and many people on the street you meet, you're kind of fascinated by popular physics and you want to learn about black holes and so forth. And I opened this book and I thought, wow, they're actually going to use Lisp to talk about physics. And I have no physics background at all. It was something when I was in college, I only wanted to learn software. What a terrible mistake that was. It's one of my great regrets. And I'm so happy to have had the chance to rectify that by learning some of the other sciences. And so when I saw Lisp and physics together, I decided to do it. But then when I downloaded the environment and found you had to use MIT Scheme and X Windows and so forth, and I really didn't want to install X Windows on my Macintosh again. I use Linux all the time, so that would have worked. But I have like negative associations with X Windows. I'm kind of done with it. But I don't want to wander. I'm rambling. I got to stop. Anyway, I thought, Colin, you'll really understand both of these things if you translate the work from Scheme into Clojure, because you're a Lisper, and that's going to teach you not only physics, but something else I was fascinated in, which is computer algebra. I remember the Mathematica people came to college when I was in college, which was back in the 80s. And the original versions of Mathematica were, nothing like they are today. But even at the time, there was a cluster of people who were just amazed at the fact that computer algebra was a thing. And working on this project has kind of caused me to, and I may have a chance to insert little nuggets of this, and Sam can too, to sort of encounter the creators of computer algebra, which is something that got started in the 60s. It's sort of the AI laboratory format and has marched onward to today. And so it's really been fun to kind of experience that. So that's my introduction. I hope it wasn't too long.
Well, thank you so much. Seeing your talk, it's titled, I believe it's called Physics in Clojure. Is that correct?
Yes.
Well, you could have fooled me that you didn't know any physics. Okay, all right. We'll go ahead and believe that. But yeah, I come from, SICP was the first computer knowledge I actually ever learned. Kind of a weirdo. I had never heard of SICM really until recently, though. Would you mind that I asked what are the main takeaways from SICM? I think a lot of us are probably familiar with SICP, but not as much with SICM.
You know, I can tell you that because what the book does is it starts with the principle of least action, which is kind of the idea behind Lagrangian mechanics. And I know that that's a bunch of buzzword, and it immediately, you know, if you haven't heard those words before, anyone's initial reaction would be the same. Oh, this is graduate level stuff. I'm never going to get there.
Mm-hmm.
But the book goes through it very patiently by saying that to find, the book initially starts by saying, if you've ever watched two people juggling bowling pins together, you will know that the motions of the objects that they throw are predictable, or they wouldn't be able to do it. It's not in chaos.
Mm-hmm.
And they go to understand, therefore, that the trajectory of the bowling pin must be mathematically describable, therefore. And the principle of least action says the function you're looking for is inside this integral and makes the integral have a minimum value. And that's where a lot of people would say, well, what help is that? How am I supposed to be able to figure out what function I could pop into an integral to get the minimum value? And they patiently explain the Euler-Lagrange equations, which say that that function also satisfies a differential equation. And if you can find the differential equation, then a computer can tell you what the motion would be. And that's the initial kickoff is Lagrangian mechanics. Later in the book, they pivot to Hamiltonian mechanics. And it gets much deeper. And I can't say I've 100% absorbed all of that. But for the Lagrangian part, you know, it was kind of eye-opening. They start there, whereas ordinarily in physics you would start with F equals ma. They start with the Euler-Lagrange equations, and they have to sell it to you with some numerical experiments to convince you of its validity, and that's where they begin.
I think with both of those texts, when it comes to anything Sussman, the more you look at it, the more you see in it. There's been many times you revisit and you see something new every time. So it's good to even hear you say that.
Very true.
Did anybody have any questions for Colin? Just any beginning questions? Nope. Okie dokie, then we will take it on to Sam Ritchie. So as we were talking about, Sam has a background in C and needed clojure. And from my understanding, Sam is now porting this over to CLJS, which is amazing because then we have these tools in the browser, which is as ubiquitous as you could possibly get when it comes to computers at this point. So Sam, take it away.
Okay, so you shamed me out of the gate. I actually don't have a background in C. I have family that does, but I've like gone completely down this other Lisp rabbit hole. Okay, I'll give a quick background and then I want to fill in some more color on Colin's comment on the SICM. There's this danger we have of, like, it feels like this physics book is this odd side road where Sussman betrayed all of us by, okay, we're all expecting a sequel to SICP, and then we get this bizarre thing. What is going on? But it's very in line with everything he did in that first book, as Colin and I have had a very visceral chance to experience. Okay, so I got into the software world. I went to school for mechanical engineering, so I don't really have any physics background, but I sort of do. I have kind of a few levels up. Had dodged software until after school, got into making iOS games and Objective-C, and then found Clojure as part of this deforestation monitoring project. I got into this work with some old friends and was looking down the barrel of a life of Java and Hadoop to make anything work at large scale. And I found this library called Cascalog in my search for ways to not like become a Java person, which I've gotten over to some extent. But I found this library called Cascalog, which was, I guess in the vein of what we're talking about here, just a very strange, like, space alien technology approach, in my mind, to large scale data analysis. This is a logic programming layer that you write these data log queries, and in this sort of minimal data log, and this compiles down to MapReduce jobs. So I was able to take this deforestation monitoring system and build it in these logical queries, these declarative statements about, okay, here's what a feature looks like. Here's how we would predict that some patch of forest has seen deforestation given the features, and the system just sews everything together. That led, as many roads do, to well, to maintaining this for a while, and then it turns out all these skills are useful for selling ads. So I went and worked at Twitter for a while and did that, and that pulled me away from Clojure for many years into Scala and strongly typed functional programming. But I was lucky to be sort of picked up by mentors that really kept the functional dream alive. So I spent a lot of time in that world, built a number of tools that were based on abstract algebra and this idea of really like find a small number of concepts and like, in the functional programming world, you'll lean on semigroups and monoids and things like this. Turns out you can push these really, really hard in industrial applications. So I was seeded, I think, with this idea of a really strong set of generic ideas can take you, as far as you want to go, and let you build. We'll get into this, but let you build systems where you can plug in implementations that are fairly startling to your original mundane code. So years go by. I'm currently at GoogleX at this lab that is doing machine learning work, but is filled with ex-physicists who will answer my questions. So I'd taken a run at SICM 5 years ago, and I think I got, based on my notes, to page 40 and then fell off the wagon and thought, I have no idea what's going on here. I picked it up again. My plan was to get through this book by reading it and writing about it and sharing, like, okay, as Colin thought, if I can pitch this to myself as a contribution to the community, maybe I'll get a little bit farther. And I found I was better equipped for the math, but the sharing aspect was really hard. It was very, very tough. I told myself that no matter the cost, I would get to something I could share that was not just another textbook page. And I did, but getting the MIT scheme system running in a way that would produce beautiful math and code, my goal was for someone to be able to actually use this stuff. You get an email from me. Ideally, if you're my parents who are here, someone who has no patience for install Docker, get this running, just a multi-level step of software engineering, the usual stuff we all deal with. I wanted to see if I could erase all that. And it was really, really hard. So I stayed with the scheme version for a while. I did many of the exercises, got pretty far in the book, but finally dipped my toes into Colin's port of this. I watched his talk, and there's a quote I saw recently that clear vision does not mean short distance. The immediate thought was, this would be wonderful if I could just run this in the browser. And hey, I've done a lot of ClojureScript work. How hard could it be to just change all the file extensions to CLJC and it will be up and running? I wrote Colin. He thought it was a great idea, and I began. And this took a few months. Everything totally works in the browser now. Everything we'll talk about. But in the process, I became addicted to this. Sussman's SICP is one thing, but he's really put his life into this library. I think this is everything he's worked on. He just stuffs into this library. And so as you're reading it, you see his thought process evolving. I go back and look at SICP, and exercises in that book are just things he had to build in the course of this thing he made. So I've kind of retroactively rediscovered a lot of this stuff, as Colin did too. But what's sitting in this thing that he built in the 80s that backs this SICM book is a nascent computer algebra system. It's this extensible system for doing symbolic computations, for doing really fast math, for doing numerical routines. I mean, everything, the bright shining lights of Lisp in the era when Lisp was set to be the AI language of the future, we're all looking at this same stuff together and building it. Mm-hmm. And so you see the language supports automatic differentiation, which of course is coming, up in a big way now that it turns out to just print money in the machine learning world. So all this stuff is there. So I went through this period of 1, port the library, 2, like, oh my gosh, I think I can go, hold on, my 2-year-old daughter's coming in.
Well, let's say hello.
You want to come here and say hi? Yeah. Okay.
Hi, what's your name?
This is little Juno.
Hi, Juno.
She can't hear us, but hey, Juno, what's up? Okay, I'll pick back up. This is
Great. We love families. We love pets.
the perils of remote work. Anyway, I like Colin. I mean, I'm really just seeding our discussion with things we'll talk about as we go forward. But step one is it would be great to show off this book in the browser. If we had an environment that felt like Mathematica, where I could, very, very lightly just present these exercises, that would be a nice build onto what Colin's built. I think what we both realized, what Colin knew and what I've been realizing is that this thing, by dint of being an extensible system, it basically it's this mathematical library it's interactive. It fits beautifully in a notebook. It's just waiting to be extended to all of the amazing matrix libraries and numerical work that Clojure has now. So I think we both see a lot of potential for a sort of scientific workbench, as Conrad, who's on the call, referred to this idea, that would give people like a really nice, wonderful interactive way to get at a lot of the amazing stuff going on in scientific computing today. At the end of the day, I would like to get back and really do justice to this textbook and get these exercises out. But I think this is Sussman's plan all along, is put these things out and just bait people into getting the Lisp bug and then evangelizing it to the rest of the world. And I've bitten hard. And here we are today.
That is wonderful. Random side question for you. Do you work with Peter Norvig?
No, I don't work with Peter Norvig. Because the Google connection.
Colin's Google, and then you talked about AI, and I was like, that I know that before even seeing there was a Udacity course, Computer Science 203, that really was influential to a lot of people that I know as far as getting into the style of programming. And so I just had to ask.
Oh yeah. That, I mean, definitely aware that's like all this stuff in the air is, I think everyone's sort of interested in AI and this sort of stuff. And then it takes a kernel like this to really coalesce actual work and interest. So yeah, I don't know him, but I'm sure he's in the pot of things that led me and many others to being interested in Lisp and this sort of work.
All right. So did anybody have any questions for Sam or Colin at this point? Nope. Okie dokie. So the point of this is to talk about the library and use the library. And we're still planning on doing a demo. I wasn't sure, Sam or Colin, I wasn't sure which one of you were planning to do the walkthrough.
I think we both are. So I think that I had a little bit of like a little demo of like what this can be used for, but the work that Sam has done has taken us a real step towards new stuff, and so I think we need to look at that perspective as well. And I think there are also, Sam and I we're poised at this frontier, and so there are lots of directions you can go. And I think one thing that the audience will take away from this is to see that there's like lots of room really to sort of bring some of these things, more fully together, because right at the point we've got like 4 wonderful things that can be brought together by somebody who understands, has some expertise. And I think we have a little bit of a barrier to cover, or a boundary to cross about.
Yeah, I think that's right. Together. Yeah, I think that's right. The framing from my perspective, and I think I speak for Colin, is this is a thing we both built out of love. There's no pitch here. But if somebody, like, I think what I'd love to get out of this is, I know this will resonate with other people, and the work people are doing in scientific Clojure, if it all coalesced into one, if it were all accessible from sort of a central hub, I think this would tie the community together in a beautiful way. So I personally am interested in, if anybody feels excited by anything we're talking about, like, I'm willing to put a lot of energy into helping someone get up to speed and work on this stuff. So feel potentially able to contribute as you listen to this, or if not, no problem. Just I think as we said, we both become obsessed already. So we're going to charge ahead.
Sort of, it's kind of funny because during the initial port, the point came where I kind of got what I considered the finish line, and I collapsed in exhaustion because it was pretty heavy. And then Samus brought this huge infusion of energy to the project, and it said, no, we didn't quite get the numeric tower right, and there's some simplification things that we could revise so that the things are being done at the right side of the fence and things come together more properly. And I think, like Sam, I was really surprised at just how far we really were from being able to change the extension to CLJS and just automatically be running in JavaScript. That some of the things that I had leaned on in the JVM, I had forgotten about. And I was like, oh yeah, well, yeah, that's going to be an obstacle to just changing the name to CLJS and running with it. And I watched Sam get completely to the bottom of that. And I was like, oh, I'm going to help you. Just hang on. And it's like, no way I couldn't catch up to him because he's really powerful in this environment. So a lot has happened with the code recently as a result of that.
I love to hear that the goal is collaboration here. And that's really what it sounds like, is the goal is infusion of excitement, and the goal is collaboration and to learn and teach each other. So we'll go on. We'll go with the demonstration from Colin and then a demonstration from Sam. And while this goes on, if the audience, if you want to ask your questions in the chat, I will watch that. And then we're going to have an open discussion, sort of like a Q&A, just to give everybody an idea of the structure here.
Okay, but Colin, before you go, can I just say one more thing about this SICM book?
Please speak.
Okay. So I just want to frame this for folks. I'll speak to myself 5 years ago. What's startling about this book is you go into it thinking, oh, I want to learn more about, okay, software. As Colin said, physics has this appeal in, to me at least, in the culture. It's just, well, we all live in the universe. It'd be nice to know more about it. And then you hit this wall of what seems like a grad level physics course. And certainly my insecurities kicked in to, oh, fuck, this is a math class. And ostensibly my software engineering ability comes into play, but it doesn't seem to be helping that much. So what this book is Sussman says, as Colin introduced, okay, we want to go understand how things move in the world. We know from prior art, this is simulatable. We suspect there's some analogy with computation here. And then he embarks on the process of figuring that out and getting it into software. And the way that happens is completely unlike the way a software engineer like me would have tackled this problem. I mean, rather than saying, let's write a test case, let's do test-driven development about physics. He reasons from first principles about what the world, like what sort of things should be true about the world. It should be that there's some number, you can have like a meter you put on the way things move that tells you how sensical the motion is. And okay, that meter should go, down if the thing makes sense, and up if you start to get something that looks a little strange. And so he builds up these ideas, and he's pulling ideas from calculus. And that's where the book sort of starts halfway through the story. You could imagine many textbooks that build up computational calculus and computational arithmetic. But if you just sort of pretend that those are tools in the toolbox, he ends up with this like two-liner to take something called a Lagrangian, and he explains what that is, but you could just imagine a spec written for it. And there's a two-liner that will take this thing and kick out equations of motion for anything you can describe with coordinates. It's totally stunning. Like, you'd never get there. And of course, it should be stunning because this is the culmination of thousands of years of scientific investigation. But so you read it, I think, for this alien perspective on the discipline we all do. And I think a goal I have for myself is to take this way of thinking and say, okay, this method of investigation is very different, but it really does use the same tools. The book does show its age a little, and Colin is going to remedy this in his demo. It reads, once you get through it a bit, like a guide for someone building an animation system, or like a guide for someone building a simulator. But it's a book, so there's no simulator to run. So you start to get to these things where you've described a very complicated motion, and the equations make no sense visually. But if you just were to animate a thing using those equations, we have this test case in our minds of, like this beautiful intuitive physics engine that can go, yep, looks right. And so I think that's the goal. I think that's what makes this more of a humane thing, is you get to look into the mind of someone like Sussman, you go through the book, you feel lost, but if you can pin it to the thing I'm making happen looks insane. There's no way this should work. Yet, when I just plug this small number of tools together, I see an animating system that looks totally reasonable. I think that's something to go off in the woods or lie in your hammock and think about like how we do things. And that's what we're all going for, I think. And then to take that toolkit and be able to use that as an example and point it at your problems, or take the physics simulations he's got and run them on this wealth of cloud resources that we have now. I think that's what we want. It's so hard to get understanding about things that you need to get it with a system that you understand and then be able to just move laterally just a little bit to your own problems. So that's the pitch for why a library that supposedly just powers a textbook could even possibly be a thing that we embrace as a community. Yeah, so there's a impassioned speech for why you should care about classical mechanics, even if you don't think you should. It turns out
maybe a future talk. I
yeah.
like it. Oh, and I had forgotten to mention, we're going to be talking about some complex topics. I know that we all don't have the same backgrounds.
Yeah.
So if in the future we want to review this, I will be putting this on YouTube. So afterwards, at some point, I will share the link in the chat to my YouTube channel where this will be posted. Just for everybody, if you need to review afterwards, that's how you can do that.
And drop, if you're super confused and want to know more, just drop a note in the channel and like I'll helplessly I will spend as much time as anybody wants on clojurians, like talking through as basic as you could possibly imagine. So yeah, we're against our own will going to say complicated stuff, but just come talk and we'll explain it and we'll write it down and put it in the docs and it'll be better for everybody.
Awesome. And that's the way we can help you.
I share that risk because, having climbed this hill, there's this human desire to come back and say, yeah, it's complicated. I'm going to show you just how complicated. And so I'm going to try to sort of maybe step back. So it's going to look a little bit like a wall of Lisp, and that's because I've come up with this demo that's I thought scientific clojurians, these people are going to need some science. So that's kind of where I'm coming up there. I wanted a demo that was sort of on the impressive side, but I'm going to go ahead and share a screen. Is that okay, Jordan? Ready for that?
Oh yeah, absolutely. Let's get this party started. All
right. So I'm mostly going to talk about this from the mechanics perspective, but I want to keep in mind that symbolic math wise, there's a whole lot of additional things that can be done about this, but you could think of this as kind of a canonical example of what the book is trying to get across, separate from what the power of the library really implies. So thinking of classical mechanics here, I've embedded this little video in this page, and this is on the space station there, and this guy has given a little bit of initial angular velocity to this T-shaped tool, and I hope that the frame rate is enough over the zoom for you to see that the tool seems to be executing this weird oscillation back and forth, and this motion seems kind of surprising, and the motion can be investigated by SICM-utils, and I'm going to talk just a little bit about how we would go about doing that. So we've talked about Lagrangian mechanics, which says we're looking for a function of from time to state. In other words, as time goes by, what is the state of this tool? And Lagrangian mechanics says you need to minimize an integral, and the first thing you need to do is to find the Lagrangian for the problem, and that is the difference of kinetic and potential energy of the system. And the book initially says, like most physics books do, we're just going to take that on faith. Later on, we can show that this all follows from F equals ma. But for the time being, let's just say, okay, the Lagrangian is, I don't know if I can, oops, that's what I wanted to do, is T minus V, or the kinetic minus the potential energy there. So, okay, I'll sort of come quickly through there. So it's a rotating object. So they use what are called the Euler angles, like roll, pitch, and yaw, to describe the position of the object. And then we write a little function that says, if we knew the three angles of the body, what would its angular velocity be? And that's what this function does, Euler state to omega body. So omega is the angular velocity of it. T rigid body is the kinetic energy, and the book uses the letter T for kinetic energy throughout, is just a kinetic energy, and that's going to be 1/2 mv squared, except it's rotating. So what that's going to be is 1/2 I omega squared, where I are the moments of inertia and omega is the angular velocity of the object. And so you can see we have multiply 1/2 times the sum of the squares of the components of inertia and the angular velocity, the omega. Can you all see it when I move my mouse cursor as I'm doing to highlight things? Or should I try to find a way of indicating stuff?
I think it looks good.
Okay. Now, I won't go into a lot of detail because it would take us way further into this than this should be. But I would say that the heart of the book is this function I'm pointing at the bottom called Lagrangian to state derivative. This takes the Lagrangian, which is T rigid body, because we're out of a gravity, right? And gives us an equation of the derivative of the motion. And once we have that, we can integrate. So I'm going to go to the next slide here. I pause to say that almost anywhere else you would go to talk about this problem, you would be dealing with numerics by this point. But with SICM-utils, we are still in the symbolic domain, which means that that function I talked about earlier, Euler's state to omega body, I can call that function with symbolic arguments. So up here, I've said def local. In the book, they have this concept called the local tuple, which is theoretically, it's an infinitely long tuple, which starts with the time and then the position, and then the first derivative of all the position variables, and then the second derivative of all the position variables, and so on forever. So you could think of it almost as a power series of the orders of derivative of the state of the system. And I know that's a big chunk to eat, but it turns out that for the classical mechanics that's under study in this book, only the first three terms of the local tuple are ever necessary: the time, the state, and the first derivative of the state. And so looking over here on the right, if you were to draw a picture of the body and draw those roll, pitch, and yaw angles and ask yourself, you know, what is the axis of rotation and the speed, you would get this vector over here. This is the angular velocity vector. Now, to find the kinetic energy of the system that would be in this state, again, it's a function of the local tuple, which are the time, coordinates, and their first derivatives. We would, you know, do the I omega squared, which is like the 1/2 mv squared. This is the 1/2 I omega squared. And if you work that out using the moments of inertia for the object, which are the capital I here, you get this pretty serious looking symbolic expression. At this is the point at which I, as a student of physics, would ask myself, you know, what are the odds that I would get this correct on my first go on pencil and paper? You know, I would say the odds for me are about 25% or less. Maybe that's, you know, maybe when I was in college, it would be 25%. And so when we continue to find the system derivative, which is this great big nested matrix structure. And this should make you feel like, aha, nestedness, we're in Lisp, this is beginning to come together. So it's this column vector where the first entry is basically the derivative of time with respect to time, dt over dt, and that is 1. The second entry in this vector is the derivative of the position coordinates with respect to time, and that just puts the dot over each of the space variables. Okay, and the third is, okay, and how is the velocity of the state variables going to change with respect to time? And that's this expression, and this is the heart of it. And I cheated a little bit on this, and actually there's a bug in this slide, I'll say. If I had 3 independent moments of inertia, Ix, Iy, and Iz, and I plugged that into this, the expression would be too big to fit on the screen. It would be about twice as wide as a page of paper. and it would just look like a wall of symbols, and you would say, well, we've got no hope of understanding this. So to tamp that down, I set the X and Y coordinates to 1 over, this is a lie. This should have said 1, 1, IZ to get this, but I didn't update the left-hand part of the slide, and I apologize for that. But now we have a derivative, okay? So now that we have the derivative, we need the thing. So the thing plus the derivative are going to get us to the motion. So I switched over to Mathematica kind of, I'm embarrassed by that because this system has the power to do this as well, but I wanted the graphics and all that stuff. So I've come up with a model of the T-shaped tool we saw of 2 cylinders together. I just mashed 2 cylinders together in Mathematica and asked Mathematica to compute the moments of inertia for me. And I picked it around the axis that gives me a diagonal inertia matrix, which is nice. All right, so, okay, what if we want to see it? We need an environment where there's 3D graphics available. Well, how about 3JS and JavaScript? Everybody's got that, right? But that's JavaScript. So what are we going to do? Could we translate this expression into JavaScript? And the answer is yes, we can. And I think one of the insights I had that kind of woke me up about this is to say, if you can convert the Lisp into infix notation for typesetting, you could convert the expression into infix notation for JavaScript, and that is what we're going to do, the next thing. So instead of converting to TeX, we're going to convert to JavaScript, that expression you saw, that big thing here. And yes, it's a little wad of JavaScript here. So this is sort of the output of a tiny compiler, which has done common sub-expression gathering to sort of yoke together expressions that are used more than once. And then at the bottom, we have that expression you saw on the left, except this time, I used all 3 moments of inertia in the X, Y, and Z directions. And so the expression has swelled up to this size. All right. Now we need a way to integrate this. And it's a multivariable problem, right? There are 6 state variables. There are the 3 roll, pitch, and yaw angles, and then there are the derivatives of them. I'm not sure we're using exactly roll, pitch, and yaw, but it's Euler angles. So just, I'm glossing over some of the torture of that. So I went and I cast about, you know, for an integrator that was serious for that, and I found one in Geneva by Heirer and Vonner in University of Geneva, and it was written in Fortran, and I'm old enough that I was taught Fortran when I was a kid, and so I can still read it, and I translated that into JavaScript. So now we have all the pieces together, and this is before Sam has gotten into this and clojure scriptified a lot of the things that I'm sort of hooking together manually. So we have more potential than even you see here. But what I wanted to emphasize with this slide is, it looks like we have about, you know, not very much JavaScript, right? So we've got a differential equation solver. We've got the giant function. I didn't put it back here, but the giant function is above there on top. And we're going to run the solver, and we're going to pump the state vectors that the solver produces into this Euler rotation to get the angles to rotate the model, which I've done in 3JS. And then if we click it, you're going to see that, oddly enough, there's the motion. So the motion in space we can see really is almost completely determined by the moments of inertia of the rigid body. And the odd oscillation back and forth is because we've chosen to spin the object on its intermediate axis of inertia. And that's why and so the object will therefore struggle to try to get into one of the other modes of motion, but it can't get there without you putting a little bit of additional torque onto the object. If you did, you would find the object fall into one of the stable states. So there's this stable state in which the object is perfectly happy to roll. And then there's this stable state in which the object is perfectly happy to spin. But if you try to go the other direction, you're going to find that you get this tumbling thing, and that's the intermediate axis theorem, which was known to Poinsot. I call him a powdered-wigged physicist in the 18th century. But look what we've done, to get this further. So this really is the sort of investigation that the system was designed to conduct. A classical mechanical investigation where you start with the Lagrangian description of the physical system and then you integrate it. And we've been able to put this in the browser. So the recording I'm showing you was actually done in Three.js on the browser, and I recorded my screen and dropped it into this slide. And you know, I'm going to stop now and give other people talk and questions, but I was thrilled to discover just how fast the ordinary or the differential equation integrator works in the browser. And that was the day in which I stopped being a snob about JavaScript. It really delivers for this application. The way the code comes, you couldn't ask for anything more, really. I mean, yes, maybe you could do it faster in C, but then where are the graphics? So the combination of this was really exciting to me, and so I'm gonna go back here and see if I can take some questions, maybe, if y'all have any.
Yeah, there was some discussion going on here about essentially just defining Lagrangian, and I like the definition. The Lagrangian is the difference between the potential energy minus the kinetic energy. Does that sound about right?
That's the kinetic, yeah, minus potential is how it goes. And the potential energy usually comes from gravity. And so that's why when we ignored that in this problem, as was true more or less in the space environment where you can observe that motion. You can do the experiment at home with a book, and the book invites you to put rubber bands around the book, which I could actually do to keep it shut, right? And then
here we go.
You'll find the book spins pleasantly along the long axis, and you'll find the book spins pleasantly along the short axis. But if you try to spin the book along this middle axis here, if you try to spin the book along this axis, you won't be able to do it. It will start tumbling. And if you Google this, you'll find that this is sometimes called a tennis racket theorem, because if you watch tennis players, they'll spin the racket along the long axis, and you could certainly toss it in the air and watch the handle whip around. But if you try to do it so that the racket and handle are spinning along the joint where the racket meets the handle, you won't be able to do it. It will tumble.
Yeah, Sam, you had some comments in the chat. Do you want to extend upon these ideas?
Yeah. I will do that. And I've stared at this tumbling handle for a lot of minutes. It's just so awesome. Like, so, okay, I'll throw let me just throw one comment, and then I think we should open it up for questions and people to steer us onto sane paths. So one framing here is what Colin's shown is, I mean, if you didn't know this was called physics, what you'd see here is we have this very strange looking software library. There's a strange API here. We have things named after old people. We have, you don't really have to write much, but each of these functions seems extremely dense. So what this book does and what Colin's presentation shows is that if you learn this complicated API, well, you've learned physics. If you can learn the API behind what this one function called D can do, like you really get then what the meaning of derivative is. So this is a different way to approach this whole body of work. What had I said here? Oh, yeah. So Colin framed it already, but the style of investigation here is, okay, we'd like to understand the motion of this thing, and in school, you learn F equals MA, and you study very simple systems. You study pendulums and things like this. This more turbo version of classical mechanics has properties like, if I want to represent this tumbling thing as XYZ coordinates, great. If I want to represent it as angles, also fine. If I want to represent it with some other crazy coordinate system I come up with, no problem. Like, you can just go ahead and change this, change your representation to analyze more and more complicated systems. And also, if you understand the system, like a single system, you can plug it together with other things. So you can build what Colin's shown by taking the cylinder, having the Lagrangian for that, taking the other cylinder, and then attaching them with a constraint in the middle, and on and on and on. So the book starts to get into wild things like, okay, let's model a satellite moving through some planets. So let's take a planet, let's take two planets and start rotating them. And then let's fire another satellite kind of through the middle of them so they're all interacting. And then let's spin the camera. Let's spin the entire reference frame so the planets look like they're stable. And the satellite is doing some crazy motion. And just this way of, the fact that this can be an interactive exploration, I think would blow, I mean, I know it would blow the minds of the original physicists that came up with this stuff. But all of this is an example of, this library was built on top of a core computer algebra system that Sussman had built out. And that's I think what we'd like to also share about. You've got this core thing called SICM-utils, which I guess we haven't really described yet. I'm happy to show a little bit of that after questions, but there's this extensible generic thing. It's basically a set of functions like plus, minus, times, divide, a few others, not too much, extended to many different data types and with links sewn between them. So you have all the numbers, but then it turns out these operations work perfectly well on power series, these sort of infinitely long polynomials. They work great on polynomials. There's all this stuff that is just jammed into the system. And so everything Colin's showing, effectively all of classical mechanics, all of physics, is one library you can build on top of this general core. And it turns out reinforcement learning is another, like this primitive of, I have a math library that I can extend to new ideas, like super fast matrices as they come out, or other ideas like this, is extraordinarily powerful. And another thing that Colin's demo gets at is what ClojureScript and Lisp give us is, if I can further represent my Lisp data structure, I can show in different ways. I can show it as equations. Those the math in Colin's slides was just, it was rendered from a Lisp expression. And you can imagine that animation as being just a picture rendered from some little description of what the angles are on the T handle. And what physics is doing here is taking that state, just like a React app, just like the thing that many of us are used to, and it's just updating that dictionary, which shows the angles. So all physics is doing here, what the physics library does is, okay, one, let's buy that. What are speeds? They're things that change positions in the direction they're going. And all physics does is adjust speeds for us. So if we had no physics, or if we were just in space and throw a ball, it would just go forever. This is Newton's first law. And then the physics add is, okay, well, there's these things called forces or potentials, and those will bump your speeds depending on where you are, or maybe how fast you're moving. And it turns out that's really hard to talk about, but all this Lisp has boiled it down to, I can just click on the screen and say there's some gravity here, there's some electric potential here, and this is a declarative way of working. All I want is that if I've got something moving, please update the speeds for me, and I'll take care of doing a little tick of the positions based on my speeds, because that's easy enough for me to handle. I can't do the other thing. Animation and all the stuff that comes out of it is just show me pictures of the snapshots, and then my brain will sew it together into a movie. So yes, Jordan, I'll pass it to you, but I think questions and steering and what people would like to see. And I'd also like to hear what people, why people are sort of here, like what is intriguing about physics or this wider thing.
Okay, so we have a question here from Theodore. And the question is, how do you represent the kinetic and potential energy before you have a coordinate system? Can you parameterize on what you want? I think you had angles as parameters in the rotating example. And the context of this question is, I'm not used to not having a coordinate system. So the question is, how do you deal with that?
I wanted to thank Conrad for his comments, because they're exactly on the money. That's the Lagrange system says you get to choose your coordinates. The price you pay for your choice of coordinates is you have to be able to represent the kinetic and potential energies of the system in terms of those coordinates and some of their derivatives. And often that's exactly what you want, because Conrad's point that if we could ask the system, and it's actually interesting to do so, to do this in Cartesian or XYZ coordinates.
Yeah.
If you do, the first thing that will happen is you'll get the spinning pizza while the simplifier deals with this explosion of square root of x squared plus y squared plus z squared. That'll just be over and over and over and again. Whereas the coordinate you really wanted was r, the distance from you to the center of mass. And so the expression for that with Lagrangian mechanics, you can have a coordinate called r, which is specific to your distance from the sun. Instead of saying, well, the sun's at the origin and I have x, y, z coordinates, the square root sign will come in, and that will hose any hope you ever had of simplifying the expression into something that you could reason about.
Mm-hmm.
Oh, can I add to this too, that that's true. One thing that's highlighted in the book, so about this coordinate system thing, is the original result that, well, okay, forget that. You can take the stuff we learned in, or that shows up in intro physics textbooks that, okay, kinetic energy, we can talk about what that means, but it's 1/2 mv squared. So you can just write that. You don't have to do anything special. I mean, Colin's already written it in a different coordinate system, but if you do this in Lisp, just write that. And then they show very beautifully in the book that because, well, okay, so that's written in terms of, say, x, y, z coordinates, or just x, y if you're in the plane. I can then write a separate coordinate transformation that says, okay, I really want to be in r and theta. I'm going to try that. That's just a suspicion I have. And so you can see this is really an interactive process between you and the machine. You say, okay, that sounds good. All I have to do now is say what x, y, and z are in terms of those other coordinates. So in the plane, like, okay, my x, I'm going to have some angle. And so it's r times the cosine of that angle. And then y is, r times the sine of that angle. It's incidental that I happen to go from 2 coordinates to 2. I can then take my r cos theta and just plug that in for x, or you get the computer to do it for me. So I compose these 2 functions, and then I'm happy to talk about, r and theta, no problem. So you can one, like, write the thing out that you find and the equations get harder and harder to deal with, or you can take these coordinate transformations and just chain them together. And another very surprising thing that falls out is you can hide constraints inside the coordinate transforms. So say you have a circle, so r is always 1 in this case. Well, instead of x equals r cosine theta, just say x equals cosine theta. And then you've done this switch where you started with x and y in your Lagrangian, so it's very easy to understand. And then you wrote this coordinate transform that's also very easy to understand, but actually only has one number that drives the x and y. And if you ask the thing to simplify the equations, it will all fall out as just a function of theta. So you can build up these very complicated things as small, understandable pieces that are all very clear. And so I hope this addresses the question of which coordinate system or y. It's like, the way I've worked in this system is I always just start with the x, y, z, because then you have this out of the box 1/2 mv squared for a point mass, no problem. And then potential energy, maybe it's easy to describe. You just sort of pick whatever you find in the textbook. Gravity makes more sense with r and an angle. And then you fiddle with it and you get them to match, and you can sew them together once they finally do. So then you bring in your muscle of abstraction and separating components into physics. Usually you have to do that in your brain if you find that trick. So it's not as helpful a trick, because you actually do want to pre-simplify, and you'd rather have like a lookup table. But in the computer, you want components, and you're happy to have the computer simplify for you.
Yeah, that makes a lot of sense. And we are getting close to, this is a 2-hour session, but we are getting close to 10, and I'm not sure what everybody's time commitments are. And so because I had told everybody earlier that a recording of this talk will be available on YouTube, in the chat, I am posting the link tree that has the link to the YouTube channel where this will be posted. So just in case anybody has to drop off, I didn't want to do it at the very end. I just wanted to get that out there. So sorry to interrupt that. I just want to make sure everybody has that resource. Did anybody have any follow-up, any response to what Sam was saying? Okay, all right. We have another question here from Keys. And he was saying that this seems very valuable. And why is this not used more in academia by physicists? Do don't they understand Sussman's body of work? Why is this not high? I'm guessing, I'm going to add on to your question, why is this not more highly regarded in academia? Or do they have some other competing tool that's more useful for their specific requirements?
It's I think Colin can jump in here. I just want to say I'm very happy that Conrad is helping us here. Conrad is like Conrad is one of the original, the OGs, the heavy hitters of numerical computing and physics. And we spoke recently, and Conrad was able to casually drop that he was around at the genesis of this Python explosion of scientific computing and was pushing some of the early stuff. So there's like Conrad's the god kind of hovering behind a lot of this.
I see.
Among the others that we encountered during our journey. I've talked a lot, so I'll just give a short one and then open it. But there absolutely are competing tools here. There have been not many, but a number of computer algebra systems. And you see this, people knew this needed to be a thing immediately. Well, back in Babbage's day, this is why let's stop the pencil on paper thing when we don't need it. Mathematica is, I think, the world-class answer. Software package that can do all of this stuff. The thing about Mathematica is it's really a closed system. Stephen Wolfram has built this thing. It's immensely powerful, but you don't see it much. I mean, I'm really interested in sharing and publishing and, eventually getting to a spot where we build things like these coordinate transforms and they're able to just be available for anyone else to use. Like, I'd like to build something that's at the root of more of like a Wikipedia style thing where the actual things embedded in the page are executable and you can depend on them. And so to explore those ideas, you need to break out of the Mathematica world. But the particular approach you get from Lisp, I think Mathematica is heavily Lisp based. So all this stuff exists, but it's a bit fractured and proprietary. And as with all this stuff, there's no new ideas. So, there's sometimes repackaging makes new things possible, but there's absolutely no claim that I think Sussman would never say that he had developed all these ideas. There's sort of ways to put things together that make immensely powerful work possible. But the core ideas have been here for, the stuff Colin's talking about is, of course, hundreds of years old.
I wanted to amplify that point a little bit because Sam jogged my memory about Mathematica because it was quite a long time ago. I thought about trying to implement this in Mathematica. In fact, it was my first idea. Now, I don't claim to be a Mathematica expert, but I want to tell you one key insight I got. It is not as easy as you think to replicate Sussman's argument in Mathematica because he is missing this thing that we in this group on this page. I'm looking at these people. If you love clojure, then you understand the power of a function as an argument to another function and building this thing, things like continuation passing style, things like higher order functions. They're sort of present in Mathematica and sort of not, because he doesn't have lexical scoping of variables. And a lot of times when you ask for Mathematica to do a differentiation, for example, you have to tell it what symbol you would like it to differentiate with respect to. And it's not, and so you can try to, again, it was so long ago that I can't really necessarily convince you of this, but it is damnably frustrating to try to represent this work in Mathematica because of its overly pattern-based architecture. I want a function that closes over variables and that, that builds a structure and, has an immutable handle. All the things that we've come to sort of love from the Rich Hickey worldview, they're not actually, that Mathematica predates that by quite a distance, and it is not there. And it's the lack is felt immediately. So one of the things that I think Sussman has got that is really kind of special is to say we write functions of functions because the Lagrangian in effect is an operator that transforms a function into a differential equation, which is another function of time.
Yeah, those those are good answers. And I think we all know, if any of us as programmers have worked with mathematicians or physicists, I know a lot of us do a lot of data science things, that it can be very difficult to try to nudge and convince these people to use these tools because they seem very complex. And that's something that we're all trying to tackle as programmers, I believe. So we have a question from James. And he said he's not sure if now is an appropriate time to ask, but I'm going to ask. So it's sort of a meta question about the development process. He's curious about Sam's comments regarding generics and category theory, and how that being a key part at integrating the complex system in the library and the roles that they played there. Can you answer that question for us, Sam?
Yeah, I can do that. Let's see if I can share this screen. If I can't, maybe I'll ask Colin to show his, but sorry, everyone, just give me one sec.
Because that's a heavy part of your background. You said working in type systems and category theory.
Yes.
I remember that correctly? Yes.
Yeah. Okay. Let's see. I think I need to restart Zoom to make this work. Colin, hold the crowd for 1 minute while I come back in.
I'm gonna hold the crowd by telling him a story about you. Okay. And,
okay. Sounds good. Yeah. Nice. See you in a second.
I was just gonna say that at one point in this project, I thought maybe stronger typing would be a good thing for this project, and we could reveal more of the type structure of physics. And so that's actually one of the goals that Sussman states, but of course he's working in a very dynamically typed environment. And so I took a stab at maybe taking some of the core things and trying to give them a Scala feel, but I've stopped that now because if the author of Algebird isn't interested in doing it in Scala, then I'm not going to try, right? So that was my joke, because Sam is like a real type level guy. So if he's happy to work at a dynamically typed environment with this, then I'm just gonna be happy. So I don't know how far I would have gotten. Probably not very.
One other thing
it's interesting to think about, if you're in the strong type world, what is the type of the differentiation operator, because it turns functions from one sort of arguments into functions with the other sort of arguments, right? A differentiation turns a function into a linear functional of the dual space. And if you're into this sort of differential forms approach to calculus, all of this, immediately and then you hear the call of the category theorists in the background, and in the world of this software, that is not emphasized, I hasten to say.
Okay, I'm back. Okay. Yeah, so let's see. Yeah, I think that what I heard in the tail end of what Colin was saying about category theory, that I'm not that person from the Scala world. We're not going to get weird. The draw. So let me just frame that. The draw I had back in those days, we built these stream processing systems that were based on these like scary to me sounding names of semigroup and monoid, and all this really are simple interfaces that you just probably throw away, like not that interesting. A semigroup is just a thing that you can define like plus on. I want to merge two of these things and get the same type back out. The only reason that's a notable thing to pick up is because it was highlighted or for software engineering, is because it's given such focus and attention in the abstract algebra world. You've got just an immense amount of work that people have done to say, well, what can I say about types that only have this property? Like all I knew was that they implement this interface. And this really would be like, how big a library can I build only with objects that, like, we know we can get pretty far with comparable things. Can I build an entire system on that? Maybe. Pick one interface and see how far you can go. So by leaning on some of these ideas, it's not so much that programming has to be math. It's that if you pick those interfaces, you probably can go find a lot of stuff out there where people, even just to get their paper or more references, will derive for you a semigroup. Or if there's something called an identity element, a thing I can add in that doesn't change like 0, then if you build on those interfaces versus other ones, you know you're going to find a lot of stuff there. You might come up with a great interface on your own, but it's not so obvious that it will be this universal general thing. So of course you can take that really far and deep into category theory, but I mentioned that more as a priming thing for me as I worked on this. Okay, can everyone see this Emacs screen?
You can.
Okay, so the way, I'll give a short tour of the way a library like this would be built, and the way this one's built. And I think this will highlight, this will answer this question. So the first thing Sussman does, the first thing this library does is say, okay, we know we have this thought that we'd like to do symbolic math, we'd like to do math on rational numbers, on real numbers. Let's take what usually in a programming language is a closed thing, like plus, minus, times. These are operations that are defined to work on numbers. Let's just open it up. Let's say, fine, we'll make them work on all the original stuff. But if you happen to have some way you want to extend plus that we don't know about, great, let's make that possible. So we defined a bunch of these multi-methods in Clojure, along with defaults, and I'll show what this multi-method means in this case, along with defaults wherever we can. So we call this sub just so it doesn't clash. It's kind of annoying to remap all the minus and times, but yeah. So if you can provide me a subtract implementation, great. If you can't, well, I'm going to lean on your negate implementation and your add implementation, and so on down the line. So we have this stable of things like plus, minus, div, multiply, quotient, square root, remainder, modulo, and Sussman just has a whole bag of these. There's lots of trig functions, but you could keep adding to this set as you want, if you want. Choosing these ones means you're giving someone the experience they expect from a math system. And the challenge this poses to the user of the library is, okay, go find other things that work here and let's extend. Okay, so let me first just show this. So I can say, 1 plus 2 equals 3. Maybe this is a better first test, 1 plus 1. Everything will kind of work like you think. I can square, because why not just name common things? I can cube. And what the library's done, though, is it's extended these functions to work with things like symbols. So a symbol here will represent itself as, like, this is an abstract number. If I add 1 to it, there's no clear thing to do. So it just keeps the symbolic representation around, and you keep going. I can go ahead and cube 1 plus x. I'll get this. All pretty pedestrian so far. You also can force the system to, you can force this thing. I think this will work now. Well, this will work later. This is something I'm working on now. You can force it to not evaluate numbers, but anyway, the system starts with numbers and then it extends to these symbolic expressions. And symbolic expressions get you immediately into this whole rabbit hole of, well, if you looked at the equations Colin showed, they can be very, very complicated. You can pretty quickly get yourself into a mess of things like, actually can't remember if this simplifies, but let's try, minus 10. Yeah, so like x plus 10 minus x. Okay, well, the x should be able to go away. So actually we can call simplify and like that'll kill it. Simplify can do other things like if I do cosine squared plus sine squared, this expands out. But if I go ahead and ask the system to simplify this, great. Look, it knows about trig identities. It turns out that when you go to this to me, like seemingly straightforward idea of let me just delay the evaluation and leave x's plugged in, the whole art and science of simplifying these things down as the equations get more and more complicated becomes pretty mind-boggling. And so that's not something the user has to care about initially. You just say, plug in symbols, no problem. Oh, let's see questions. Yeah, so it does term rewriting, and Colin can jump in if people want more details. It also has two other simplifiers, which I'm just beginning to wrap my head around. So Colin, correct me, but one is this rational function-based simplifier. You get things into canonical form as a ratio of two polynomials. And I believe if you factor these out appropriately, then you can cancel things across the fraction bar. Oh, sorry. Okay, let's see. Daniel's saying, yeah, so sine, okay, so Daniel says it might be useful to explain how the sine and cos simplification actually works and mention how sine and cos are defined. So sine and cos are defined just the same way that add and, if I look here, I think sine. Yes, so they're just defined as generic open things. There's something called sine, there's something called cosine. And if I implement them, let's see. They're implemented like this. You just say, if you give me a real number, which in Clojure is, in Clojure on the JVM is just any of your types, whether it's a fraction or an integer or a floating point. Well, we have support for that. Just call out to math/sine, no problem, or math/cosine. So for all the stuff you know about, all of this machinery just gets passed right through. You don't do anything. But then for symbols, all that happens is this happens. Like the system, it's a little more complicated because there's simplifications that might happen, but it just gives you a list with literally like a little tag there saying, at some point, if you get around to it, if someone plugs in something for X, please evaluate this for me. This is what I mean. So it's just a hint.
Sam, can I interrupt with a quick follow-on question here for the
Yes.
development process of this? Okay, so
Please.
I think that the value of the expression of this is undeniable, right? In making certain ones of these expressions readable. Now, I've gone down this path before in Clojure with the generics, and I have written code that reads beautifully, and then I come back to it 6 months later and I realize I have no idea how it works because with the lack of a type system and the dispatching, some of the behavior becomes wait, what did this thing do? And then the jump to source doesn't necessarily make it easy because you've overloaded the operator a number of times. I was curious if you ran into that when writing this, and if you have a way for managing these sorts of changes without a type system, or if you just have a clearly defined way of doing this in your head to prevent yourself from shooting yourself in the foot when doing this sort of category work without a compiler time backup.
Yes. Okay, great question. Let me address that. I also just want to note for Daniel. Sorry, Daniel. I believe this particular simplification comes from there's a rule-based substitution engine that looks for certain patterns and replaces them with things that like identities they're equal to. And there's a whole art to this. There's, in this case, you first need to shuffle something into a form where like, okay, it's not quite right. Like what if I have 10 in between? So the system has to go gather terms that are exponents of sines and cosines, get them together enough that the pattern can recognize them and kill that and replace it. So we leaned a lot here on what Sussman had built and cherry picked out the optimizations that seems like they made sense. But you see in his library, there's many, many different attempts at what are good rules. There's for different problem domains. Maybe you want some set of simplifications. You want to expand everything out. Some you want to gather terms and identify things that look familiar to you. So with this, the real name of the game is make a big expression, cancel everything out that's obvious, using rules like this, and then go try to put things in different forms and see if obvious cancellations show up, and keep looping and looping and looping. And then finally, when you don't change anymore, spit the result back out.
Yes.
Okay, so about, I don't think this is a solved problem. I mean, obviously, about once you have this open dispatch system. We've kept ourselves in line now by just leaning on, okay, for math, like we've got this numeric tower, we've sketched it out, it's not that complicated. So we're pretty convinced it's correct. But even now, problems come up like, okay, you need to make sure that the, one thing we ran into was the symbolic expressions and numbers, the defaults for symbolic stuff would grab numbers and prevent their evaluation. And this, I think, came from like my lack of understanding of how Sussman had built the system. So I think dragons lurk in this approach without a type system. I have hopes here that we can come back and sort of take the core that's well understood and gradually type it and put enforcements here. But one more comment I'll make is Sussman's response to this, which I don't subscribe to, I'm not like terribly happy with, is that he gave a talk on a paper called Building Robust Systems, and he says, look, I thought about this for 60 years. I don't think there's like a totally general solution, and I actually think that we shouldn't look for that. If we want to build these immensely complicated systems that look like biological systems, we're going to have to be comfortable with things that break and fall down. And, in a world where you have at every memory location a processor and they're all just kind of trading values, you're going to get errors like something assumed commutative multiplication, and then you passed a matrix in. And this is like kind of unsatisfying. He basically said, hey, this is really hard and let's just not worry about it because squishy biological systems do just fine. I hope we can hold off the madness a bit longer with some judicious application of specs and gradual typing. But yeah, you may look at this based on your prior experience and say, oh my God, I see the wall you're about to run into.
I think that you're right that in the Sussman code, there's an almost flagrant refusal to consider the type of anything. And as someone who's a little more open to typing things in the FP world, I'm sort of in the middle, right? I'm a middle of the road guy when it comes to type. Certainly I've dabbled in Haskell and had the experience of thinking I understood it and not quite, and having to go back and fix it, and you learn something by doing that. That's the Haskell experience for me. But but going from Scheme where there's nothing, right, to Clojure where there's protocols and def type and so forth, we were able to layer in a little bit of the typing using the Clojure tools, and it was very refreshing to be able to do that, right? To say, what is this thing, because it implements a protocol, and I can do it that way instead of having what I call if polymorphism, which is what you get in the Scheme world, where it's like, is it a duck? Then it quacks. Is it a whatever? And they also use some Scheme hacks, some MIT Scheme extensions to sort of endow objects with behavior in a way that's not really part of the Scheme specification. So in MIT Scheme, there's this thing called an apply hook, which says, if you are an object and you find yourself in function application position, in other words, if someone is asking you to call yourself, like to call you as a function, what will you do? And you can set an apply hook on the object in MIT Scheme. And that's not part of the R5 RS or anything like that. But in Clojure, we can say, you can implement IFN, or capital I, capital FN. And that means that you are a function, and you then get to implement apply as the fulfillment of that interface. And that's how we do it in SICM-utils. And I'm much happier than I would have been if it were something else like that. Back to you, Sam.
You're on mute, Sam.
I said there's many directions to wander off into, but I'd love to be steered by there's a question actually above that we had not gotten to.
I was actually going to didn't want this to get lost in the sauce. There is a question from Keys here. Yes. I think we're getting into this now. Could you say more about which directions you would like to see this develop into? For example, probabilistic programming. We've done a lot of talking about the past and what Sussman had kind of intended in physics, but you guys wrote this tool. What do you see are the applications, and where would you like to see this go?
Great. Oh, I'm so glad you asked. So I think there's a menu of different things to build off of this base. And let's see. There's a menu of things to build off of this base. So one is, let's say you didn't want to think about the future. You love Mathematica and you love that approach, and you're just deep in symbolic math. Of course, one way to go is to extend this to other mathematical types, and it becomes this place that you can go, this playground of investigation. James, I think, mentions here. Yeah, okay. James, you're like a plant in the audience. This is amazing. The place I want to take this, and the beauty is we can go in all these directions. Okay, so one is do traditional mathematical things and make this feel more like Mathematica. Two, what do we have that Scheme doesn't have and that Mathematica doesn't have? We're hosted on the JVM. We also compile down to JavaScript. So we have hooks into all of the incredible work that people have done on visualization, on ultra-fast matrix libraries, on Python interop, on Julia interop now. I just saw it drop. There's a libjulia-clj. So many of these systems, I think, maybe this will be controversial, but a lot of these systems have taken off because there's a core, very, very fast library or some abstraction you have access to that just opens up an entirely new field. A lot of the Python work hooks into TensorFlow and PyTorch in modern machine learning. We have this ability to drive GPUs and TPUs and do unbelievable levels of parallel computation. And all of that in Python comes from this abstraction of a matrix that if you do matrix operations in a library like JAX, I'll drop that name. Really what you're doing is you're combining, these things are abstract objects and you're combining them together, and then the system will compile the computation you've expressed, just like we see here, this symbolic expression, down into instructions that actually get run in the GPU in this intermediate representation. So SICM-utils is a driver potentially for all of that work. If you want a system that can go ahead and do like incredibly fast modern matrix computations, we have Neanderthal in the clojure world. So we already have a matrix type here, but it's a native built out of clojure sequences. That deserves to be much faster. We have core.matrix. All we need to do is extend these generic operations to those types. And what that looks like, just to be quite concrete, is don't glaze over too much of this. Basically, you just need to tell me how to perform each of these operations on your type, and then potentially between your type and other things already in the library. So complex numbers, great. Most of these are built in. You just call the thing in the underlying type. If I want to add a real and a complex number, great. I have to turn here. I flip the order, but you just have to tell the system how to go bind in your thing to what already exists. And you don't have to do that. That's the beauty of, you can play fast and loose if you want. You can just implement a few and then you're off to the races. So smoking fast matrix math will let you get to a world where you can explore things symbolically. You can play around with abstract matrices, and then you can run your code on Paula. Our complex numbers also represented as phasors. I actually don't know what a phasor is, so I'm not sure. But clarify for me, and then maybe Colin can jump in, or anybody else. So if we do that, you have this explorable workbench, and then you can go run things on a big iron machine, and you can be pretty confident that they'll all work. The other direction to go is the browser. I think that we're in a world where often we learn about things in almost a toy system. You build up a thing in JavaScript so that you can visualize it, but then you have to go rewrite it in something to actually run it on a big cloud machine. You see a lot of machine learning demos that build up neural nets, but you didn't really learn the real thing. You learned this, you learned the idea, but then the actual thing that runs on the to make your job happen, to train your net, is very different. So because we can jump platforms and because each platform has access to smoking fast stuff, where I'd love to take this is a world where everything runs in the browser, just like Colin's demo. We have visual representations. We add to this extensible math operations, extensible visual representations. So I just have a whole library of dumbbell and bar and point and t-handle and all the stuff you can play with. They all have Lagrangians predefined. Coordinate transforms are already predefined and in here. So on top of the main thing, a toolkit of things that can visualize themselves. Colin's already shown that we have an animator already. And if you visualize things at different ticks, you get animations for free. And then you can take the same code that ran your animation and say, this will be contrived, but I wonder if the t-handle does something different, if I run it for 100 million years. That is absolutely what Sussman's research was all about with solar system dynamics. Let's get a feel for something, see if it looks right. And then let's switch to, in his case, very specialized hardware he built called the digital orrery, which I'm sure is like a tiny piece of a phone now. And let's run the solar system for 100 million years and do that with many different initial configurations and just see what happens. And I mean, it's stunning almost to think that you could debug something in a visual language and then behind the scenes be running it on, switch to JVM mode and have your dynamic thing that runs in, say, a notebook interface, just waiting for maybe keyframes of that or results to fill in on a chart. So this has absolutely been done in Scheme. It lives in Mathematica, but the amount of work people have put into, Blender and these visualizable 3D systems is just completely mind-boggling. So using a system like this as a driver for that is something I just want badly for myself. And I think that eventually, ideally, you get to a world where you just explore and you find a thing. And if you don't have to leave the system you use to do the exploration and then actually ran everything, then there's no need to publish a paper that's sort of just a PDF or write a blog post and deprive people of the ability to play with the thing you made. You made a discovery, you found an interesting thing. It happened to be a thing you built that people can explore in ways you never understood or thought about. So we want to get to a space where it's not that everything needs to live in SICM-utils. It's that SICM-utils is like a depot for all these ideas. And it's not so obvious that I could use power series together with numbers, together with visual language, together with all this. But if you smash them all together in a mildly sane way and try, then you get this tool for thinking that I think is pretty different. And then you can leave too. I mean, you don't have to, because all this stuff works the way you'd expect with numbers, you can break out, no problem. So that's a sketch, I think, of where to move.
And we did get, did you see the answer to what a phasor is, Sam? Paula had responded.
Oh, got it.
Just copy pasted from Wikipedia.
Yeah. They are. Yes, got it. Yes, we do represent, let's see what Jordan says. Yeah, it's e to the I theta. Yeah, we have this, they call it like the polar representation, but that, I mean, they're leaning behind the scenes on, yeah, absolutely. And a lot of the simplifications depend on, we'll push things into that representation and then, and do calculations in phasor representation and then pull back out. Yeah, I'm totally on board with everything's a phasor.
So we also have some questions from Daniel that I don't want to get lost in the sauce again. He was inquiring about seeing if we can tell a bit about the definition of a derivative. And he also contributed some thoughts on the D-type next library, but maybe I'll let you answer the derivative first and then we can move on to the other one.
Colin, you want to jump in?
I will. Although either of us can answer this well, because I know it's a very active thing, but we use what's called forward mode automatic differentiation. And I'm glad you have this, Sam, this picture up of def method here, because there's another type called a differential, which represents as infinitely small increment of a number. And we define the math on those in a very special way to help us compute derivatives. In other words, it's very much like a differential form. I don't want to overcomplicate it, but let me try to, I'm going to just scratch that. I'm going to start over. Imagine if instead of calling a function with a variable x, you could call a function with the variable x plus epsilon, where epsilon was a special kind of number that was programmed to, whenever it multiplied epsilon together to form epsilon squared, it vanished in a puff of smoke, leaving only the linear part behind. That's the arithmetic that has been erected on these differential numbers. And so if you have these numbers, and literally we take x plus epsilon and send that into the function and get the value back, and the resulting value will now have a mixture of constant and linear terms in epsilon. And if you drop all the constants and then set epsilon to 1, you find you have the derivative, and that's how it works. So that's why it's called automatic differentiation. In other words, we don't implement the chain rule. The chain rule comes about by calling a function of a function that got one of these epsilons as input. The epsilons know how to combine with plus, minus, times, divide, and every other operation. So we know what sine of x plus epsilon is in terms of cosine, because that's what you would expect. And so in order to extend this thing over the type hierarchy, you need to explain what it would do to a differential number if you know. And if you do, then the automatic differentiation works. So it's really kind of fascinating.
Let's say too, Colin, let's maybe both give a take on, let's just go to what is a derivative at all? Like, what's this idea mean? I think I'll give two ways. The way you may have seen this, if you have fuzzy memories of doing this in the past, is if you've got some curve in a plane, then the derivative here is the slope of that curve at a particular point. Now, that's not like hugely informative. I find that that's true. And we can go through like why that's true or how that got the initial idea up. But a different way to think about it in a more general library is, say you have a function that kicks out a number, just as an example. So this could be great. This could be a mathematical thing, like tell me the area under this curve, or just the position. This could also be something like, I want the transit time of my airplane as a function of all these different numbers that go into my autopilot system. Or it could be like the cost of some good as a function of all of just a ton of different inputs to some huge function. You don't have to be able to visualize this at all. So what the derivative is first, let's say you have one input. So there's one number that goes in, one that comes out. The derivative of that function is a new function where when I give it a number, the thing that comes out is how sensitive the output was to that particular input at that spot. And at that spot matters because like you may have a different answer for, let's see, if you may have a different answer for different inputs. So if I say, tell me I'm doing a trail run. I'm on a mountain. I'm at a particular point. There's a value at the point of my height, say my height above sea level. So what the derivative would tell me, in this case, I have like let's say my X and my Y position. I can ask for the derivative for the X or for the Y input. And what this tells me is how sensitive is my X position, or is my vertical like height above sea level to my X position? Concretely, if I move left or if I move right, am I going to go up or down, and how fast? If it's like very high positive derivative, that means I have a wall to my right. Very high negative, there's probably a cliff. So what this tool gives you is the way this is used in machine learning is you've got all these knobs set inside a big composition, a bunch of matrices that get multiplied, millions or billions of these things. And you can say, my output is some number, like, is this a cat? What's the probability? I want to nudge it down. a differentiation system can tell you, how do I adjust every single one of these knobs to make my output more likely to go down? Does that make sense? There's what happens if I change the inputs? What will happen to the output? But then you can go the other way and say, I want to make the input go down. Which direction should I move in? I'd like to go up the mountain. Which direction should I move in? And automatic differentiation, what Colin has described is, it turns out this idea sounds really different from all like normal arithmetic, but there's this a complex number is like a number with two parts. There's an imaginary part and a real part. So you can think of this as like a point in an XY plane. There's an X position and a Y position, or in this phasor representation, there's like a length. Just think of it as a 2D vector. There's a different thing that it's a number, but it's got two components. And if you define all these operations between them in a particular way, and the way is, okay, the second thing has this property that you imagine it's multiplied by a little tiny thing like a delta. And the delta is so small that if I multiply it by itself, it goes away, like just as Colin said. If you find that trick, then the derivative is a thing that will like pop out. When you get your result back, the two-part thing becomes the function value and then the derivative value. So they come along as pairs together. And what's nice is they'll work through loops. It works inside containers. Like you can make tuples and make sequences, you destructure them. All your clojure stuff like just sort of works around this idea. It's totally insane. And again, in this like synergy thing, if I pass in a symbol to my derivative, oh, should we do a demo?
Yeah, please. You should just do a couple of Ds there in your REPL, Sam.
Here we go. Sorry, Colin, I got excited. So, okay, here's a simple one. Let's say I have my cube of X. Oh, look at that. It's X cubed. I think I can do, does this work here? Well, forget that. I was going to make it display pretty. People like Lisp notation here. Okay, so if I cube X, I get X cubed. One thing you may remember is to take a derivative of like something that looks like this. You move the exponent down and you take one off the exponent. So this should be 3x squared. So if I say d of cube, oops, sorry, I get a new function out. And d of cube, if I pass x to it and then simplify that, is 3x squared. Pretty simple example, but I don't have off the top of my head like a crazy one to do. Let's see, just imagine I like bowled you over with some immensely complicated thing. And you knew that you'd worked on it for hours and oh, the system just told you. Yeah, what's wild about the system is Sussman and Colin after Sussman have baked all of this idea of derivatives into, I'll answer Keith's question in a second, into this thing D. And you pass D a function and you get out the derivative. It's crazy. It's crazy because you're not restricted to things that feel like they came from a calculus class. You can pass in anything you want. And you say, what does it even mean? Like, I want this output number to go down. Okay, let's find the derivative. And I just want to know how sensitive I am to different inputs. Take the derivative. Go for it, Colin.
No, I'm sorry. My mouth moved accidentally. Please continue.
Oh. So this way of working is unfamiliar to me outside of the domain. And one thing I think the physics does is it starts to give you examples of how to incorporate this concept. And then the idea is we can break it out of that more traditional application. And quickly, just for Keith, you said, is there still a use case left for symbolic and numerical differentiation now that we have auto diff? We do have numerical differentiation here too. One case is just to check how different your expected result is. Like you can trace, this works by routing through the whole function and accumulating results as you go. You can check if there's anything funky going on by actually probing around the value you want the derivative at and saying, okay, what's my value here? What's my value a little to the right? And that just appears as a nice way to check your results, but I think not really. And symbolic you get for free out of the system, as we just showed, because the thing you get, like the derivative that follows along, is built out of generic calls. And so if I pass in X, then it's going to follow through, and you get for free, really for free, just through the design of the library, a symbolic derivative, along with the problems that come with that. It might be a really complicated expression, but then you can attempt to simplify it down.
And for anybody that wanted some more background derivatives, there is the lectures that go along with SICP. Sussman covers the derivative rules just as part of the lecture. I've posted that link there. So if you do want to know more about derivatives, there you go.
There's one thing I wanted to add, if the dog will permit, I don't know, but this system is actually has a very, very solid implementation of derivatives of functions of several variables, and even nested forms of functions of several variables. So that if you ask for the derivative of a function of multiple variables, you will get back gradient of the function. And if the function, if you do it with a higher order function, you'll get the Jacobian back. And so it's pretty slick. Another thing, if you're into physics to the point of knowing the difference between a covariant and a contravariant vector, you will be delighted to learn that this library takes that notion extremely seriously, and the different kinds of vector are encoded in the system differently. So an up tuple, as they call them, represents a column vector and is contravariant with respect to coordinate transformations. And if this is not ringing a bell, just ignore it. But it is a kind of a safety net for some of the type issues that you might have. So in this system, we think of functions as being functions of things that happen in space. So they're functions of up tuples or up vectors. If you differentiate such a function, you get a down tuple or a covariant vector, which represents a linear functional. In other words, like Sam was talking about, what is the derivative really? A derivative takes a function and gives you back another function, which takes an increment of the original value and gives you the increment back of the result of the function. And SICM-utils and SICM-utils handles the multiple variable both on the input and the output. So if you have a function from many variables in to some other number of variables out, you will get a matrix of m by n differentiated arguments. And it's pretty smoking hot if you've ever labored through sort of a calculus of multiple variables thing and maybe not quite been sure about it. This will help you remember that in a hurry, right? I mean, it will force you to go back and understand what was really going on there. And definitely in my case, it deepened my understanding of it.
Okay, so we had a request for a gradient example, and you all just watched me kind of fumble through this.
Yeah.
So we've got a function here that returns three things. So an up here is it's a tuple. You can think of it as a vector with three.
Column vector is the best thing to say about up, I think, at this point.
Fair, column vector. And we can, I guess we can just show that. Great. So we've got this, apologies, we've got this. Let me get back to my REPL. Yeah, so we've got this thing. I guess you all can see this. I'm just blocking it with my camera. That's the symbolic representation of this thing. Okay, so if I have a function that takes an XYZ and returns this tuple of XYZ with some operations applied, I can take the derivative of that and I can pass it three things. And I'm going to get back, in this case, a down tuple with the derivative with respect to each of the outputs inside of it. So you see all these things. Colin, you want to feed me a better example for where I should go?
That's about right? So what happens is if you multiply a down tuple and an up tuple together, you'll get the dot product automatically because they are in this perpendicular relationship to each other. And if you've ever studied tensors, you'll know that the down tuple has down indices and the up tuple has up indices. And so what happens is the system applies what's called the Einstein summation convention. And you're in the playing with the big boys if the word Einstein comes out. But it all again, I want to stress for the people who don't have a background in this, that this system doesn't force you to learn category theory or tensors in order to get where you're going. But if you have studied physics, again, and I learned this coming at it from the complete back end, because I don't have a physics background, I really don't. But you'll get a warm feeling because you realize that, in Mathematica, there's no distinction of this type. And that's a strong system, where the variables, where the vectors remember their or contravariance from the point of view of coordinate transformations. It's really sweet that it does this. And if you know what I'm talking about, I think you got to be impressed that someone went and did this. And so when we talk about the system as being sort of fairly weakly typed in terms of computer science, yes, but in terms of mathematical thinking, it's actually typed in a way that many expositions of physics gloss over, fudge, mislead the reader, we don't want to frighten the undergraduates kind of thing. And so it comes back to you that, that we're using more of a little bit of a more principled approach to differentiation than you usually find in situations like this. And, a book that kind of opened my eyes about that for me was a book by Harold Edwards called Calculus, a Differential Forms Approach, where they say, no, really, it's not that hard to start from there. Also, if there's Spivak's calculus on manifolds, which is very imposing, very threatening, feels like you're going into deeper water. But I like this system because if you found that rough sledding, the system basically takes care of it for you automatically, and you don't have to know. And the things that you want to be able to do just work out with a little bit of additional type information that turns out to be kind of cool. I guess you could show the matrix form if you had a function that took an up tuple as an argument and returned an up tuple as a result. Is that what you're aiming for?
Yeah, let's do that.
Yeah.
Let's just take, we can just add I think we just add a destructuring form here, right?
I think you can.
And then do this and get rid of this.
It did the same thing because it thinks those are the same thing. What you want to have, well, you've got a matrix of results, right? A down tuple of up tuples is a matrix.
That's
right. So
this
is a Jacobian. It just happens to be diagonal. If you were to like you had square x cube y and exponentiation of z, why don't you change z in the exponentiation of z to z plus y? And that will cause some some more fun, right? So now
there we go.
Now we have it. Now the matrix isn't diagonal anymore, and that's good, right?
And
So
here's where we get to like what we're looking at here is I'm going to reformat it a little bit, and I don't have my REPL able to display tech, but like this is where an interactive mathematical system, you want to be able to just, it's required that it be able to render. This system can do it, but my terminal is not set up to render tech natively as equations. And further, you want to extend that visual language beyond. I did email Sussman with this. A fun thing about this, as Colin's found too, is that you can write prayers to the old gods through email and they'll respond to you. I found a bug in his LaTeX renderer, and he says, "Oh, it's amazing. It's lasted for 30 years." And he goes, "I don't actually look at LaTeX ever. I'm so comfortable reading math as prefix notation that this has just never come up for me." So I think it's possible to not need the crutch of what I'm doing here, but I'm not sure anyone's going to reach that level who didn't come up in Sussman's lab in the 80s. So there's so much. Let's see. Oh yeah, so I see Daniel's question. Jordan, is there anything else we should cover that
Yeah,
further up in the stream?
we're coming in on the last 10 minutes of this. I think we went over some really super fascinating things. I did want to ask you, Sam, I was just typing this up, but I'll just ask you verbally. These last couple of examples before they go away in your REPL, will you just through email or through chat, just copy paste them to me? Because I'll include them in the description. That way people
Yes.
can experiment with running it themselves.
I'll stick them in a gist after
Perfect.
we jump off.
Perfect. So we have a couple of questions. So as you said, Daniel, maybe we can discuss for a couple minutes the possibility that we get on these topics in one of our study groups. So yes, on the weekends, we have these study groups, the machine learning study groups. And it looks like there are some wonderful applications of this library to them. How many people would be interested in doing that? Right, yeah, we can raise our hand. You can say in the chat. I'm not sure the best way to, okay. So we do have some interest.
Maybe I'll just comment briefly that
Yes.
If it makes sense to people here, then maybe we can organize a group that is dedicated to learning, reading into the code, reading into the books. So if you wish, please reach out. You have our email and let us talk about it. Thank you.
Yes, and on, I hope that most of you guys have the link to Cycloge github.io, and that is where a lot of the Cycloge information is posted. I will post that in the chat for those of you who do not have that, but that's where, and also we talk about it on the Clojurian Zulip. So if you are currently on the Slack, I highly recommend getting into the Zulip. And we have this question from Keys here. What about the integration with Maria Cloud and Rome Research? And Sam, you said you want to take this one?
Yes. So let's see. I don't have this running now. There's just so much to go into. But what Keys is getting at is Colin and I have been talking with there's three main developers of this wonderful interactive notebook system called Maria. So Maria is, okay, so port this to ClojureScript, and then what do you do? This has to live somewhere. We'd like to make this available so that we can write the examples we just showed or lessons. We want an exploratory environment that people can just play with and ideally send links around. And ClojureScript is magical. The code can just be running when you open the page. None of this kernel backend stuff that is fine and necessary, but tough. So Maria is a notebook system that is built in fully self-hosted ClojureScript. Anything, let's see, I can move through in the browser and just evaluate stuff as I go. I mean, see, oh, look, I've made a square. I built a circle. They've also have this, we won't go through this now, but they've got this beautiful system for doing functional reactive programming baked in. So I can define a cell and then I can subscribe to that cell, think spreadsheet, in other functions. And if the cell's value changes, all the updates will propagate out. So there's one primitive. And another is that you're able to extend visual symbols or visual representations to things. So a square here returns a thing that Maria knows how to render. Okay, so those two together are pretty powerful. All we need to get an animator is take SICM-utils, put it into the system, and have the physics engine, just like Colin showed, updating some cell, and then the animation will just happen. So that was my target. I wrote to the Maria team. They're basically, we're working now on getting this deployed in Maria so that all these examples will just work. So what'll happen in fairly short order, now that all the tests passed and this all works, is you'll be able to go to Maria and play with this stuff there. The Rome research comment, like the next step beyond this is we'd like to be able to explore in a notebook and then actually develop physics applications in the notebook. And I think what that requires is if I come up with something interesting, whether the interesting thing is some visual representation or a coordinate transform or something like this, I'd like to be able to make a new page and just use the code from the old page. And all of this should work because Clojure is beautifully serializable. Everything can run in the browser. So there's a bit more there's a bit of a technical challenge there, but the idea here is that this will be kind of a next generation notebook thing where let's see how far we can get with sort of a live Wikipedia that I can go depend on text, just like if you've seen Rome Research, I can make sort of, well, we won't get into that, but imagine hyperlinks could also be function dependencies. Then you start to get this thing that can grow out, and we don't have to cluster around the little fireplace of my REPL. It just becomes easy to make things and share and actually build on the work of others, not have to start all the way from the beginning, understanding calculus, understanding physics. A tinkering mindset would open up with that. So that's the pitch, but it's like no sweat now for the Maria team now that this all works. So expect in the next few weeks or month or so that we'll send an email out and say, hey, everyone, if you want to try those examples, they live on this page now, and everything lives on this page. You can do everything Colin did. You know,
and how would we sign up for those emails?
Well, I think I'll send to you, Jordan, and then hopefully we can broadcast it to as a cycloge follow-up.
Okay, that's
that's a good question though. We right now we're in the clojurians. I see what you're feeding me. We're in the clojurian Slack channel at SICM-utils. We made a channel in there, so we'll say things there and broadcast them out. And then if there's better ways to do it, we need feedback, and we want to talk about the stuff in a way that people interested can hear. So
right now I do find it helpful. I follow USAM on Twitter. I know that a lot of tech, it's so hard between Facebook, Instagram, all the things. Twitter does seem to be a pretty good resource though for a lot of the people that I know they're on there. So if you want to maybe paste your Twitter handle in the chat for anyone that wants to follow you, that would be beneficial. And is it pronounced Case? Is that how we pronounce your name? Case?
It's pronounced Case. Yeah.
Case. Okay. Well, we apologize for mispronouncing it.
Now that I'm talking anyway, let's take this opportunity to thank you guys for this, because this was amazing. Like, I've been following this for a long time, SICM and Maria Cloud, and trying to tinker away, but feeling that I don't have enough skills myself to really pull stuff like this together. I had another question about Maria Cloud. I've seen an issue on Maria Cloud where they were talking about requiring any CLJS or JavaScript library. Will SICM-utils be like part of this self-hosted, and so it's like an added library now, or will they expand such that you can require any library?
First step, they're going to add it. And it's, I came into this not knowing anything about computer algebra. Now I know more. I know that has to happen again with self-hosted ClojureScript and how you can live pull in dependencies into a running system from outside. Jack and Matt, who run Maria, I mean, Matt, he makes that sound not that bad. He just needs an excuse to do it. So at first we'll just, there will be nothing to do. It'll just be in the system. You may have to, we'll probably make it so you have to import, like opt in, so you don't nuke the existing picture language that's there. But it'll just be part of the base distribution. For these animation libraries and things like this, of course, then that's going to require solving this problem of external dependencies. And I think a page depending on another page is going to have the same problem. So I want to be able to treat ideally every paragraph or every form as its own potential dependency or namespace. I think if we get that solved at either of those levels, the solution will push out. And thanks for following along. I mean, this started out of anxiety that I was learning all this great stuff and couldn't share it with anyone except Colin, of course. And you're wonderful, Colin, but we need a, it's a super heavy lift to get anything working, even just to get a Clojure toolkit going. So bear with us, and the goal is to make it and crack the whip on us to make it easier.
And we are reaching the end of time here, but I would like to extend one more opportunity for anybody to unmute your mic if you want to say anything directly to Colin and Sam. now is the time. For those of you that are interested, we can stay after to maybe talk about some practical applications, some study group stuff, do some planning. If anybody's interested in that, we can stay a little bit after. Personally, I'll have to jump by 11:15, but for anyone that's interested, it doesn't have to go immediately. We can do that. So I will open up the floor.
I think you've done a great job moderating this, Jordan. So I want to thank you both for having me and Sam, and for getting this rolling and all that.
Yeah, thank you so much, Jordan. Thanks, everybody.
Thanks
I'm
to
happy
Daniel.
to stay as well.
And indeed, thanks to Daniel for conceiving this idea in the first place and getting this together. It's been a lot of fun, and I've really enjoyed the chance to meet all of you in the grid here.
Mm-hmm.
Thanks all.
Now, after watching this, does anybody have, was anybody sparked with excitement about how they're going to use this in their life? Case, you said that you've been following this for a while. What are you trying to apply? I'm fascinated to see the application of this.
Yeah, well, let's see. I think it started all with some of these explorable explanations that I found online from I think Case or Nick Casey or something like that, and that just blew my mind. It was something about shelling points, and how you can, the parable of polygons. I think how you can have, like, in a society, how even if nobody chooses to be scared of another group that doesn't look like them, even if, like, everybody makes small decisions, like I'd rather live next to somebody that looks like me, then you get like this segregated community. And it was just so friendly, and step by step you just got this deep insight that I was really struck with that. And then I saw all the stuff from Brad Victor, and and Michael Nielsen has some really cool stuff written about this, where he actually also talks about SICM and how it's really cool, but that there's no, like, visual representation of it yet. And then Jupyter Notebook. I'm a data scientist myself, so I've been using Jupyter Notebook a lot, testing out actually the next journal as well, and observable. But the thing with observable was, like, I still felt it was kind of like in this contained world, difficult to productionize. And I'd rather not use JavaScript. And so I've just been looking for this way of, I felt like there were always good reasons why it was difficult to really dive into it and communicate something without being an expert JavaScript person that would just build their own thing. So I see so much potential here, and I kind of have the same long-term vision as Sam has. Like, I would love it if this can just be this aggregator, this thing that kind of snowballs and propels everybody forward, because there are so many small examples that people can start with, and can just fall into success, fall into understanding, and just this accretion of high quality material. So I think that there's a real niche here, real void, and it's been hinted at since the 60s that something like this would be super valuable, but for some reason we've never really quite gotten there. And that's and so it's super exciting that maybe this might be it. Yeah.
Oh, awesome. Thanks for giving some feedback. So we are having a discussion here in the chat, the infamous Slack versus Zulip, the battle of them. So yes, somebody had mentioned that a lot of the data science and machine learning, a lot of the discussions that we have in the clojure happen on Zulip. And from my understanding, a lot of the conversations from Slack do get mirrored to Zulip. I'm not sure when or how that happens. I just heard that at some point. I went ahead and I didn't see that there was a SICM-utils stream in Zulip, so I just created it very quickly, but I'd be interested in hearing what everybody has to say on that, specifically Colin and Sam, since it's kind of your jam.
I had never heard of Zulip, so I will look into it.
Yeah, I'll go hang on both. That sounds great. I mean, there's all these, yeah, I think that's very easy for me to sit in both. Yeah, this whole proliferation of things is its own problem, and let's not confront that. Let's just adapt for now. There's other problems.
Sounds good. I recently made the switch, and it was pretty seamless. Zulip is nice.
Can I file in a complaint at this point to the
Please, yeah,
to the organizers and to the speakers?
Mute.
Because no, but you did such an inspiring job. I see all those hours I'm gonna spend nerding, geeking in this library, and that's a big chunk of my future life.
Oh,
Yeah,
we're sorry now.
Yeah, hey, yeah, unfortunately, we're already too deep down the rabbit hole. So we
went all the way to the bottom, so you don't have to.
Or to provide companionship when you get here. Yeah, I know. I had the same conversation with Colin, and we should put a disclaimer on this that it's not your average. Yeah, it's a wormhole. It's so bizarre. There's so much in here. Case, I think you're. Yeah, I just want to highlight. I think that's right. I think Colin's very animated by this too. It's. I mean, I talked to someone recently who said all this work at the end of the day is about mitigating loneliness. Like, we learn all this stuff, and then we're forced to jump between representations to share it, and that's all fine, except that you get these fractured, research results and things that are very, very difficult to penetrate. And I think that you can't solve it for everything, but there's a big class of problems where it would be much, much easier to lateral between fields and actually get up to speed in something that seemed impenetrable if we just had a growing kind of mass of shared models and so the goal here is to provide an example of that, and hopefully it gets cannibalized and everybody eats it and observable takes it. Like, if we can do a nice job here, I think, and come up with an implementation of this idea that's in line with what you're referencing from the 60s and 70s. We can either definitively find out why that can't work, or make an honest run at it and provide a demo that other people can take and steal for their own systems.
I think you make a really good point. That's something James and I talk about a lot, is how lonely it must be to be an advanced particle physicist, when it's, maybe like you and 3 other people in the world know what you know and you get excited by it. And I really like the point that you made about combating that loneliness by sharing this knowledge together. That's a really wonderful thought, a really beautiful thought to end this on, I think.
Thanks, everyone.
Thank you.
Colin and I will be in both those channels, and I'll put our emails in there too, or I'll ask Jordan to help us send out a follow-up. And yeah, please come talk and hang out. And you'll probably run into trouble because like this library is confusing, and I'm furiously working on documenting it, but treat us as your AI guides through this thing. And we're both happy to help. And
I will share the links of this recording as soon as I post them. It'll probably be a 3-part, since this is a very long meeting.
Okay. I'm gonna drop out there. Yeah.
Bye.
Thanks for having us. I had a really great time.
Well, wonderful day, night, afternoon.
Theodore.
Hey, Daniel.
Hey. How are you?
I'm good. How about you?
Is it a good time to ask how you are?
Sure.
Yeah, and I hope they edit that out before going to YouTube. Oh, maybe I can stop recording. Yeah, that if it makes sense. And then no need to edit this out. Oh, I'm not the host. So we are recorded, and they will edit it out.
We could jump into another meeting if you...
Yeah, right. Yeah. So see you soon.
Okay.
And yeah.